Hi everyone, this is our third and final video on linear codes. So today we're going to be talking about perfect codes, which, as the name suggests, are good and efficient in a certain sense. So first, let's see what we mean when we say a code is perfect. So we say that an R error correcting code sitting within strings of length n is perfect if the entire collection of strings of length n can be expressed as a union of these neighborhoods of radius r centered at the code words. Okay, so maybe it's a good idea for us to have a visual on this. So what you might imagine is this rectangle as being our entire collection of strings, Bn. And within that entire collection of strings, we have our code words. So they're sort of scattered around here. And we know that our code is R error correcting, which means that we can draw around each one of these code words a neighborhood of radius r. And when we do that, none of these neighborhoods are going to overlap. Okay, remember we learned that a couple of videos ago. Now, in ordinary circumstances, if you take these code words together with these neighborhoods, they are not going to make all of Bn. There's going to be some gaps, in the middle, some strings that are not in a neighborhood of radius r centered at some code word. But in a perfect code, this collection of neighborhoods fills out the entire collection of strings. And so what that means is that every single string on Earth is within radius r of some code word. Okay, now another way to say a code is perfect, or an R error correcting code is perfect, is to say that it achieves the packing bound, right? So remember, the packing bound gives us sort of an upper bound on the size of an R error correcting code. And it says that the size of such a code times this number is less than or equal to 2 to the n, which remember is the size of the set of binary strings of length n. And in the case that the code is perfect, we, instead of getting an inequality here, it's just plain equality. So that means that the size of the code is as large as it can possibly be. So one might wonder, well, how do we construct such things? I mean, these are things that are obviously the most efficient, R error correcting codes. So how do we construct them? Okay, we're going to be focusing our attention here on perfect 1 error correcting codes in F2N. And the first thing we should probably do is figure out which values of n could possibly admit 1 error correcting codes. So that's the point of this theorem on the slide. It says that F2N has a perfect 1 error correcting code. So if that happens, then n must be 2 to the m minus 1, and the size of the code is 2 to the m minus 1 minus m for some whole number m. Okay, so where are these numbers coming from? Well, remember from the previous slide that a 1 error correcting code must achieve the packing bound. So that means that the size of the code times n choose 0 plus n choose 1 must be equal to 2 to the n. Right, so remember here in the packing bound, we're stopping at n choose 1 because we're looking at a 1 error correcting code. Okay, so let's simplify this a little bit. This says that the size of our 1 error correcting code times 1 plus n is equal to 2 to the n. And then if we solve for the size of the code, we get that it's 2 to the n over 1 plus n. Now, if we look at that quotient for just a moment, we'll see, the size of the code is a whole number. And that means that 2 to the n divided by 1 over n, 1 plus n, must be a whole number. And the only way that can happen is if 1 plus n is another power of 2, right? The only divisors of 2 to the n are other powers of 2, right? So therefore, Therefore, 1 plus n has to be equal to 2 to the m for some m. So what does that say about n? Well, you just solve for it here. So n must be 2 to the m minus 1, right? And remember, that's what we asserted about n in the theorem. And now let's solve for the size of the code. Right, so the size of the code is 2 to the n divided by 1 plus n. Remember, we already knew that. But now let's plug in n equals 2 to the m minus 1 and see what happens. So n is 2 to the m minus 1. And then 1 plus n is 2 to the m. And then if we just use laws of exponents here, we get that this is 2 to the m minus 1 minus m, just as was asserted here in the theorem. Okay, now what that says is that if C, this one error correcting code, happens to be a linear code, then its dimension is this power on 2. Namely, its dimension is going to be 2 to the m minus 1 minus m. So if we have a perfect linear one error correcting code in strings of length 2 to the m minus 1, then the check matrix for that code must have this form, where the matrix has 2 to the m minus 1 columns. All right, so why must it have that form? Well, remember that the check matrix for a k-dimensional linear code in F2N has this form. So it's H equals, some matrix A next to the n minus the identity matrix of size n minus k by n minus k. And this thing is going to have n columns. Okay, so all we need to do is replace n and k by the appropriate values for perfect linear one error correcting codes. So if you replace n and k by n equals 2 to the m minus 1, right, like what we had on the previous slide, and k equals 2 to the m minus 1 minus m, well, what does that do for us? Well, n minus k, so if you take n minus k, then that will just give you m, right? N minus k is equal to m. And so the I n minus k becomes just the m by m identity matrix. And then how many columns does the matrix H have? Well, we're told it has n columns, but n is 2 to the m minus 1. So we get 2 to the m minus 1 columns there. Okay, and that proves the theorem. Now, the question is, does such a matrix exist? Remember, in order for a check matrix to correspond to a one error correcting code, we need every single column of H to be non-zero, and we need to have non-repetitions in the columns. So sometimes, as we saw in a previous video, sometimes it's impossible to form such things. And so this is an important question for us, is does such a matrix exist? So the answer to that question is that it does exist. So at the top of the slide, we have the theorem that we stated and proved on the previous slide. That is, if C is a perfect linear one error correcting code in strings of length 2 to the m minus 1, then its check matrix has this form. The question is, does such a thing exist? And in fact, it does. So a check matrix H described in this previous theorem does exist, and its columns just consist of the 2 to the m minus 1 non-zero members of F2m. Right, so remember, the columns of H are strings of length m. And if you look at the totality of the strings of length m, there are 2 to the m minus 1 non-zero strings in F2m. So anyway, a perfect one error correcting linear code formed in this fashion is what's known as a Hamming code. So here we finish this video with an example about Hamming codes. So in part A, we are given a few values of m, and we're asked to determine the string length n and dimension k of the corresponding Hamming code. And here maybe the best thing to do is just simply make a table, right? So here we have m, and then remember n is 2 to the m minus 1. And k, the dimension of the Hamming code, is 2 to the m minus 1 minus m. So those quantities can head our table. And so our values of m that we're to consider are 1, 2, and 3. And now we just need to compute n and k, right? So when m is 1, n would be 1, and k would be 0. So what this means is that in this very small case, we're looking at strings of length 1, and the code is of dimension 0, which means that it consists just simply of the 0 string. Okay, when m equals 2, n would be what? Well, it would be 3. Right? And then k is 4 minus 1 minus 2, which would be 1. And then when m is 3, this would be 7. And meanwhile, k would be 7 minus 3, which is 4. All right, and we could continue for more values of m if we wanted to, using these formulas. All right, so that's part A. And then in part B, what we want to do is give a check matrix for a 7-4 Hamming code, C. Now, what does the 7-4 mean? Well, that is, 7 is the length of the strings in which the code words appear, and 4 is the dimension of the code. Okay, so we're going to be looking at the case where m equals 3, right? Because that's where our n is 7 and our k is 4. Okay, now remember our Hamming code is the check matrix is the set of all non-zero strings in F2 M, which would be F2 3. So we need to just write down all these things. Right, and then remember that the last few columns of this check matrix need to wind up being the identity matrix of size 3. Right, so there we have it. And if you look, you will see that these columns of H, those are exactly, that's the totality of the non-zero strings of length 3. Okay, so that's the answer to part B. All right, now for part C, well, we're asked to correct, we have a code word V that's transmitted, and this string Z is received with at most 1-bit error. Then we're supposed to find out, what was the original code word. So you might remember how we do this. So we take our string Z and we multiply it by H. So let's put it over here. Here's our string Z, so it's 1, 0, 1, 1, 1, 0, 1. And we add all that stuff together, and we see what happens. So notice that in this matrix product, what we're doing is we're adding together the first, third, fourth, fifth, and seventh columns of H to get this product. So let's see what that is. So I get 0 in the top, and then here I get 1 plus 1. Again, I get a 0. And then I get a 1 and a 1, which is a 0 and a 1. Okay, so the matrix product, H times this string Z is equal to 0, 0, 1. And so I look throughout my check matrix H for the column that has 0, 0, 1 in it. And there it is. It's the 7th column. And so what that means is that if I'm going to correct Z, I correct the 7th bit. Okay, you might remember this from a prior video on error correction. So V then must be equal to 1, 0, 1, 1, 1, 0, 0. All right, okay, so finally now we're supposed to list several code words. And this is an interesting problem because remember, code words are ones that when you multiply them by the check matrix H, you get the 0 string. And it might be hard to guess what some of those words are. Okay, but there's a better way to do this. So let's erase a little bit of this work so that we can have room for this better way. Okay, so remember we have this check matrix, and it's broken up into 2 parts, right? We have this matrix A on the left, and we have the identity matrix on the right. So remember early on in our discussion about linear codes, we learned that matrix A can also be used to produce code words, right, through this matrix that we had been calling E. right? Where on the bottom you have matrix A, which in this case is 1, 0, 1, 1, 1, 1, 1, 0, and 1, 1, 0, 1, right? So that's this matrix right here on the left side of H. And then on top of A, so this is our matrix A, on top of A, we put an identity matrix, and the only one that will fit is the one of size 4. Right, so this is our I4. Okay, so if we want some code words, we form this matrix E, and all we need to do is to take some linear combinations of, columns of E. In fact, the columns of E themselves are code words. So, like, for instance, the first column, 1, 0, 0, 0, 1, 1, 1, that's a code word. The last column, 0, 0, 0, 1, 1, 0, 1. That's a code word. What if we added a couple of these columns together, like maybe the first and the third column? We could add them together. That gives 0, 1, 0, 1, 1, 1, 0, right? So anyway, this is probably the best way to list off members of C, is to pull off that matrix A from the check matrix and then set it below an identity matrix to form this other matrix E, whose columns, when you take their linear combinations, will give you the code words.